Hi, everyone. We would like to welcome you all to this talk of the IEEE GRSS-APS-SSCS Joint Student Chapter at the University of Southern California in partnership with LabNet and the IEEE USC Student Chapter. Today, we are pleased and honored to have this talk presented by Fram Akiki, titled Introduction to Semiconductors. Fram Akiki is the president and co-founder of Joint Technologies and has over 35 years of experience in the semiconductor and electronics industry, including executive assignments with IBM, Qualcomm, and Siemens. Fram holds a BS in Electrical and Computer Engineering from Clarkson University and an MS in Electrical Engineering and an MBA in International Business from the University of Vermont. He has authored several white papers, holds a patent on RFID cellular connectivity for the IoT market, and is an adjunct instructor at Clarkson University and Cal State University. Fram, we would like to welcome you again, and the floor is yours.
Thank you very much. Thank you very much. What's so great about her introduction is I didn't have to tell her how to pronounce my name, and she did it beautifully. So thank you for that. It's a pleasure for me to be here today. I want to, first of all, thank USC. I would also like to thank all the various chapters and divisions of IEEE. I know both undergrad and graduate level. I'd also like to thank LabNet, which is the North America's premier Lebanese technical professional society. All three of them basically got together to help sponsor this event. So thank you very much. I also, you heard I'm an adjunct instructor, and I teach 3 classes this semester. In fact, it's one of my busier semesters doing that as an adjunct. But at Clarkson University, I'm teaching a course called Introduction to Digital Transformation. So I promised I would do a shout out to that class, go Clarkson Golden Knights. And my 2 classes at Cal State University, I'm teaching Management Information Systems and a class in Telecommunications and Networking. And shout out to both of those classes, go Cougars. I guess I don't have to tell you a little bit about my background. The only thing I remembered as I was driving up here, I'm based in San Diego, and as I was coming up, I actually remembered that if you go back to my service date when I first started with IBM, et cetera, I just went over 40 years of experience in the semiconductor industry. So all this white hair that you see here has been well earned in this industry, because I look out here and I don't see anything. It's all still there. So what I'm going to present to you today is kind of a stripped down version called Introduction to Semiconductors. And this came out of a course actually that I taught last semester at Clarkson University with the same name, Introduction to Semiconductors. And it was a course that I had thought about and actually developed and finally kind of launched with Clarkson's help. What I noticed was for people that were interested in the semiconductor industry, there was a lot of material available around what I call very sort of highly technical stuff. Like if you were interested, if you were a chemical engineer and you were interested in chip manufacturing, you could take courses on chemical vapor deposition. And if you were a designer and you wanted to learn more about formal verification and in the design process, all those things were there. But I had actually a lot of people from outside the industry say, hey, Fram, we're hearing more and more about chips and semiconductors, right? It's in the news now. They're bringing, fabs back to the US, and everyone's talking about chips going into cars and all this stuff. And so somebody should do a real basic introductory course around it so that we can understand, what's the industry about? And so that was the course that I did last semester at Clarkson. And it was a course that was a combination of lectures that I did and interviews where, again, because of remember the white hair I mentioned, I had a lot of colleagues in the industry, some even at the CEO level, that I could reach out to, and we did fireside chats. So it was a seminar lecture kind of course. Clarkson actually opened it up to people outside of the university who wanted to audit it for free. And through the combination of the students on campus and outside, I actually had over 1,000 students in the class. And got a lot of great feedback. And the students, by the way, were, people that were getting their PhD in electrical engineering, arguably, knew more about this stuff than I did, all the way over to folks in political science, because they were hearing about, all the geopolitical stuff that was going on with chips, and they felt like they needed to understand the industry a little bit better, to people in construction, right? Because all these fabs that are being built in Arizona and Ohio and New York and whatnot, they really wanted to understand the industry better, even though they were, laying concrete or putting up girders or whatever. So without further ado, I'm going to jump into this. And obviously the first presentation that I had done, it was 2.5 hours. So I added a few more slides so I could, because Michelle told me we've got 3.5 hours, right? No, no, I've cut slides out and I may skip some as I go through it. And hopefully there's something for everyone, right? For people that are highly technical to people, that maybe not technical at all. And I'll try to touch a lot of different bases here. Okay, so what are semiconductors, particularly when we talk about it in the context of chips and whatnot? And the simplest analogy I like to use is that, these small little chips, they have things on them called transistors. And I liken the transistor on there to a switch, just like the switches that you might have in your house or apartment. And just like your house, when you wire up all these various switches, they can perform functions, right? You can turn things on, you can turn things off. And basically that's what a transistor does. It turns on and it turns off. And, there's even different kinds of transistors. You might hear people talk about digital or memory transistors, right? And these are transistors that are either 0 or 1. Right? So like some of the switches that you have in your house, right? Turns the light on, turns the light off. You also have analog or mixed signal transistors. And these kinds of transistors act like switches that are sort of like dimmer switches. And, the dimmer switch, you can not just turn it on and turn it off, you can kind of get some intermediary state there. And so, by the way, of the electrical engineers here, has anyone actually ever wired up a switch or something like this? We got a few heads shaking, so that's good. That's good. Most of you in this room, based on looking at age wise, probably don't recognize this, or maybe you saw it in some legacy thing, and that's a vacuum tube. And the vacuum tubes were the predecessor to transistors. And these things, by the way, were switches as well. And if you go and you pull out a very old radio and a very old television, you could actually see these vacuum tubes in there, and they acted as switches like transistors. The other great thing was with these, if you were like where I went to school, right up by the Canadian border in New York, and it was be 40 below zero, these things were great because they generated a lot of heat, and they could heat this room while still doing that switch function. And, we get to the modern day chip that you see here. This is one of the Apple M series processors. And, you look at these chips, they've got 25 billion plus transistors on them, right? So 25 billion switches in something that's about the size of a penny. And these switches, again, they get wired up to do various type functions that you see here. They can do processing, right, which is kind of what your brain does, storage and memory, communicating, etc. We'll talk more about this. All right. When you look at the history of the semiconductor industry, and I'm going back about 40 years here, this sort of corresponds with my my legacy and history in the semiconductor industry. But there's always been this tight relationship between the electronic industry and the semiconductor industry. And you know, people would say the electronic industry is what drove semiconductors, and some people would say no, semiconductors are what enabled electronics to happen. And so the first instantiation of this was what we call the compute era. Started like with mainframe computers, and ultimately it led to, you know, one of the first iconic devices that we all have here, right, which is the laptop computer. And you know, what really allowed the laptop to happen were innovations in semiconductors, two semiconductors in particular, right? The processor and memory. You know, putting those two together kind of really forms the heart of the laptop. Next, we had the connected era, and of course, big iconic device there is the smartphone. And you know, that built on the compute piece with the processor and the storage, but it added in the capabilities of communication, right? And of course, I think the School of Engineering here is the Vertubi School of Engineering, right? And,
like the advanced computing one?
yeah,
There is a new center right now.
but Vertubi was one of the co-founders of Qualcomm company that I worked in, right? Very famous from the communication side. So a lot of legacy around communication here on campus in USC. And finally, a lot of people are talking about a third wave, and again, will drive semiconductors. And it's around the intelligent phase, right? And we'll talk a little bit more about this. You know, this is kind of under what everyone talks about today, right? Artificial intelligence and the relationship with semiconductors. So semiconductors, right? Been around for 40 some odd years. A lot of the demand for it was driven. If you would go in and like listen to analysts speak, or when they tried to kind of understand what was happening in the industry, they would look at two big channels. They would look at the laptops and the smartphones. And now you hear a lot of people talk about chips going into everything. Diversity of demand is sort of the trend. And you know, we see that here with some of these new markets, right? Everything around AI, machine learning, and probably even more general data centers, hyperscalers, right? So all of this stuff is driving incredible demand for chips. The whole smart and connected, right? Refrigerators are connected, washer and dryers are connected, Fitbits, all these things, right? Have chips in them. And of course, automobiles, you know, there was a big crisis, if you remember, during COVID, where there were automobiles sitting on lots waiting for chips, right? So an interesting thing here, right? I'm sure a lot of people see this. Within 5 years, 50% of the cost of an automobile is going to be based on electronics. So you have something that was primarily a mechanical instrument, and it's quickly becoming electromechanical. And I'm not even talking about EV here. This is just a normal gas-powered car. This is a chart, looks very complicated, but I like to show it because in addition to chips going into a lot of different markets, if you take an electrical system that's in any of these markets, right, whether it's the smartphone or the laptop or something new in autonomous vehicles, and if you analyze something called the bill of materials, which is, you know, all the things that make up that system, what you're seeing is a gradual increase on the content of those electronic systems that are coming from chips. So the chips are not only going into various markets, within the markets that they go into, they're delivering more and more value. So this is like a doubling effect, if you will, as to why chips are becoming so popular and important. The semiconductor industry is one of the most innovative industries that's out there. If this was something I pulled from 2024, and it looks at venture capital funding of various industries. And by the way, if you had looked at this probably 5 years earlier, you wouldn't have even seen semiconductors show up on the top 10 list. So they're one of the ones that have jumped up the highest. And as you can see, last year, over $8 billion went into the semiconductor industry from venture capital. And that's one measure of innovation. Where's that money going into? Well, AI is probably the number one place VCs are funding in the semiconductor industry. The other is in connectivity technologies, wireless in particular, 5G and 6G. By the way, I just attended a meeting on 6G, and in case you're interested, they're talking about roughly a 2030 introduction of 6G. So about 5 years away. We usually get a new G in wireless every 7 to 10 years. They also usually stick around for about 20 years or so. So that's why you always see overlap at any given moment. You'll typically have at least 2 or 3 of those Gs operating together. The other thing to look at in terms of innovation is the companies that are in the industry, how much are they spending on R&D? And you see, if you add up all the research and development being spent in the semiconductor industry, it's about $120 billion. As a percentage of revenue, it's about a $600 billion industry, right? So you're looking at about 20% R&D spend as a percentage of revenue. That percentage, by the way, is the second, I think it's the second highest industry in terms of revenue. Again, I'll put a shout out to my niece, Christine, who's in the pharmaceutical industry, because they're actually number one. They're closer to 24% on the as a percentage of revenue. But again, the combination of R&D and venture capital money, right, is at least a couple of metrics that show the innovation going on. This is a slide I like to use, and you can see there's still some blue highlighted there. These were the companies where my guest speakers came from. So you can see I tried to cover all the various segments and whatnot. I start actually over here on the right-hand side, the semiconductor equipment market. And you can see some of the big players here. These are the companies that provide the very complex equipment that's needed to build chips. But interestingly enough, if you go into Dun and Bradstreet, kind of keeps these official industry categories, the semiconductor equipment folks are not technically considered part of the semiconductor industry. So when they talk about the semiconductor industry being roughly 600 billion in size, it's everything this to the left. If you include this in, which I kind of informally like to do, then you're talking about 720 billion. So the 600 billion, all over here, you have the folks who are enabling the design work, right? So these are companies as part of what's called EDA, electronic design automation, right? Synopsys, Cadence, Siemens. They provide the software tools that are used to design chips. And then in addition to them, there are people who will provide some of the key intellectual property blocks, design blocks. When people design chips, when companies design chips, they don't necessarily design everything from the transistor level up, right? And they look for ways to get to market faster and more reliably. And what they do there is license blocks of functions from various companies that allow them to put their chip design together faster. And who does the design? Well, you have two kinds of companies that do designs. You have what I'll call the original classical company called IDMs, integrated device manufacturers. So these are people that do both design and manufacture. You can see some of the companies there. I'm sure you probably recognize. something that started to develop in the 80s or 90s was sort of breaking this apart. And you heard about this thing called the fabless model. And this is companies that focus strictly on doing only the design, and then they send the design to a contract manufacturer to have them built. And of course, Qualcomm, who I worked for 12 years, is part of that group. And, you know, sending to various, what's called foundries. All they do is contract manufacturing. They take designs, they build them, and they ship them back. All these chips have to be packaged up so that if they're going to go into an electronic system or down onto a board, they got to have a package around it. So all of this is about 600 billion. People in the industry are talking about the road to 1 trillion, right? So that's kind of where they see the semiconductor industry heading. As a comparison, you know, some of the two biggest industries in the United States are automotive, aerospace, and defense, right? Those are somewhere between 2 and 4 trillion right now. So you're looking at the potential semiconductor industry, you know, quickly becoming one of the larger industries. I'm not going to go through the whole supply chain. Okay. What's interesting about the semiconductor industry, and the reason I start with manufacturing, and it's, you know, I don't want you to think it's in deference to my brother Greg, who might also be listening on here as well, and he spent 40 years in 40 plus years in semiconductor manufacturing. The reason I start here is because the semiconductor industry is actually a manufacturing or technology defined industry. What do I mean by that? Well, those other industries I was talking about, automotive or aerospace and defense, those are design defined industries. You design a plane, you design an automobile, and then from there, you provision a manufacturing line that can build those designs. The semiconductor industry does it the opposite way. They actually define the technology and the manufacturing process first, and then they put together some very detailed rules that they hand out to folks and say, any chip design that you want to do, use these rules because the manufacturing process and the technology has already been defined. Moore's Law, you've heard this probably time and time again. It's an important feature of the semiconductor industry. And it comes from Gordon Moore. He was the co-founder actually of Intel. And it's probably 50 or 60 years ago. He basically said that the rate and pace of innovation for semiconductors is such that roughly every 18 months, you can double the number of switches, transistors, that are on a given area of silicon. You can also use it in a different way by saying you can significantly reduce the area a given number of switches will take up. And so depending on whether you're trying to drive for more performance, so you put more switches down in that area, or if you're doing a cost reduction, right, which says, I want the same number of switches, but I just want them on a smaller piece of this wafer because it'll cost less. And it's used both ways in the industry. Who remembers the periodic table? Do we have any chemistry folks in here? Right? I guess not. So the technology of semiconductors is heavily about chemistry and elements. You have, first of all, what's called the starting wafer that you're going to build on, the base. The most common element used is silicon. And by the way, you're going to see a lot of the elements that are used are in this part of the periodic table. And if folks kind of remember what this part sort of represented, this was the semiconductors, right? They weren't the metals, right? Nickel, copper, etc. And they weren't the insulators. It was sort of the in-between. Silicon is one of the most common. We also see it combined with germanium. So you have a compound wafer, silicon germanium. You have silicon carbide, This is another sort of emerging element used. You have gallium. That's another one that's used. And of course, gallium arsenide. And all these different sort of combinations and compounds are used basically to achieve kind of different things. The silicon one is kind of what I would call the workhorse of the semiconductor industry. Most of your, base logic, et cetera. Yeah. Oh, by the way, if you do have a question, yeah, feel free to raise your hand. Some of these others like gallium arsenide, silicon germanium are kind of more custom combinations, and they're usually used to achieve certain things like extra ability to produce power. So if you're doing like a amplification chip, that's what you'd be considering. Or if it's a chip that's going to go into, for example, high reliability or a high temperature environment. Next up, so semiconductors, they have this property that says under normal circumstances, they don't conduct. However, if you induce or put things in them, you can get them not only to conduct, but you can control when and how much they conduct. In other words, you can turn it into a switch. And so you start with the base material that we just showed, and then you implant or you introduce some of these kinds of chemicals into them: boron, phosphorus, arsenic. And once you form that, all these billions of switches on that circuit, on that chip, you have to wire them up, just like in your house, right? You got to wire up all the switches. And typically either copper or aluminum are what are used on there to wire them up. And finally, in the process of building these chips, you use a whole bunch of other chemicals. Some of them are used to, clean the wafer, other gases and whatnot that are used, and you can see them here. So very much a chemical process, and this is why you see, for example, a lot of chemical engineers will work in semiconductor manufacturing. These are kind of the major process steps associated with building a chip. And I'm not going to go through all of them, but you get an idea of these different steps, how they're either depositing something down, or they're removing things. A big one will be lithography, which I'll show you here in a second. And these steps just get repeated over and over again to build the chip. I should point out that when you're doing this, depositing or removing things, it's in an extremely precise fashion. This is not like you're painting a room and you're going in there with the brush, and it's very precisely controlled. Time, temperature, pressure. Obviously, these are all built in clean rooms that are much cleaner, for example, than a hospital operating room, because the slightest flake of skin or things that way beyond what you can see can literally destroy the entire chip, right? So done in a very controlled environment. So I'm going to quickly run through how a transistor is formed. So we start out in this case with a base wafer. It's silicon. And the first thing, one of the steps I mentioned before, was diffusion, and diffusion allows us to grow an oxide. Diffusion is basically a heat process, right? If you put silicon or basically anything and leave it out in the air, over time, it will develop an oxide on it. But what you're doing here is, by heating it up, you're accelerating it, first of all, so you're doing it much more quickly. And you're doing it in a very controlled fashion, right? You want to be able to measure these things in angstroms. of accuracy. Next, you deposit another material on top called polysilicon. And then you go into one of the most important steps. It's called photolithography. And what it does is it basically is the step where you're going to transfer your design pattern down onto the wafer. So if you ever did stencils or stenciling as a kid, it's essentially a stencil process that you're using. And so there's something in semiconductors called a mask. And what happens is a mask is built from the design. So when you send in your CAD design, they build a series of these masks. And the masks are used such that there's a special material called photoresist. And when the light hits it, here and here, this photoresist, that photoresist will stay soft. And underneath the mask, it stays hard. So when you come in and later do a chemical clean process, the two places where it was soft got washed away, this stayed on there. And so what you've just done is you've done the stencil. The mask, you know, had a layer here and it went down onto the photoresist. Next up, we kind of get rid of the polysilicon, the oxide, and then we get rid of the photoresist because it's done what we've needed it to do. All of this, and you can see the various steps here, etching and lithography and whatnot. Oops. Next, we introduce those elements I talked about, boron, phosphorus, arsenic, and they get implanted in. And this is called ion implantation. And what happens is you implant it, but no matter how hard you implant, right, and bombard it, it still stays in the surface. You use another diffusion step, you drive that in. And then you come in and you put another protective piece across it. And if you look at right here, what you have is the switch. That is the transistor. And of course, this part here, right, which is sometimes called the gate, this is the toggle of the switch. And so by applying an electric field here, you can control whether this here is going to be on or off. That is the planar transistor. Now, this is what I just showed you, kind of a different representation of the switch. Now, you can see there's been lots, and we continue to have lots of innovation around new and better switch designs, right? Today, we're primarily on advanced technologies using FinFETs. And you can see there's something called gate all around, and we continue to innovate. By the way, funky designs here, but they're all basically using those 7 manufacturing steps that I mentioned earlier. You just different combinations of chemical, time, etc., to form these. Why is there innovations here? Well, the problem here is as you start to shrink smaller and smaller and smaller, eventually you get to a spot where you can't shut this off because these two parts of the switch are so close together. No matter what signal you put on the toggle in the middle, it just will not shut off. And how annoying would it be to be in a house where you shut all the switches in the house, but the lights don't quite go off, right? So that's why they've had to come up with new designs here that will, in fact, ensure that this transistor continues to operate like a switch as we go to smaller and smaller dimensions. Once you've formed the switch, you got to wire it up. And what I'm showing here is, you've got the switch or the transistor down here, and you have all these levels of wiring. And typically what they do on the wiring is the first level will go one direction, and then you put like an insulation in between it, and then you go the other direction with the second level and third level, fourth. complex chips sometimes will have 10 levels of wiring necessary to be able to hook up all these billions and billions of transistors. Manufacturing, right? If you step back and kind of look at this from a building standpoint, you have something called a wafer fab. And in a wafer fab, this is a semiconductor fab. You can see some of the steps that we have here. So I mentioned it's a manufacturing controlled industry. And so when you've defined the manufacturing process, the technology, there's these things called design kits that are typically provided to designers. And it's all the rules that they need to be able to design something that ultimately will go built here. And once they've designed it, they provide their design files in to the fab. And the fab then builds masks. And I showed you one of those in the photolithography thing, but the masks basically represent the various levels of the CAD design. These masks can range anywhere from 50 to 70 masks for a process. So when the chip is going through, you know, I showed you just kind of one masking layer, but they're using this 50 to 70 times to do everything from defining the switch to all the levels of the metal. All of that is done through these masks. They're reused typically as part of the production process. So, and if you change the design, if they discover there's a problem, we got to go change something in the CAD, that usually means you have to then build a new mask, right? And that becomes part of the process to build the thing. Whoops, let me go back here. So the fab, and that's kind of the cool term used for where these chips get built, typically is broken out between the front end and the back end. The front end is all of the steps associated with defining the transistor, like I showed you, right? Defining the switch. And then there's the back end. And the back end is usually everything associated with wiring it up and connecting it, right? So that's going to be all of your metallurgy, aluminum, copper, etc. Here is both the amazing as well as scary thing about building a chip. Okay, I'm going to go one more. Prototype through this whole process, right? You can do something really, really fast, kind of quick and dirty, because you're trying to verify things. It might take about 30 days. Production can be anywhere from 4 months on up. But the thing is, until you get to what the just start of the fab backend, when you put down the first layer of wiring and connectivity, you really don't know what you built, if it is functioning well or not, right? So usually as soon as you get into the very early part of the back end and you put like the first level of wiring is usually put down, and it gives you the first opportunity to do an inline test. And basically what it allows you to do is test some of the switches or transistors down there to ensure that you haven't messed something up. But, you know, this could be 2 or 3 months in. And if something is messed up, this can be a big problem. So this is why they have to consider backups and, you know, all sorts of things. It also tells you why it's so important to control everything associated with manufacturing, right? So to ensure that when you get here, you have a high probability that this works. When the chip is done, you do a test and you identify how many of them are good. On a typical process, right, you want this to be very high, 90% or better. And then it's cut up and packaged. They do another test, and that becomes the component typically that you see that goes into an electronic system. All right. How much does it cost to build a state-of-the-art fab? Do we have any guesses? No guesses. It's a quiet group. So it's up to $20 billion and rising. So when you hear in the news, like a fab going into Ohio that Intel announced, or Micron announced one in upstate New York, Clay, New York, and Intel and TSMC both building in Arizona. These advanced fabs, $20 billion. The largest expense that of that 20 billion is the semiconductor equipment. Remember that was that segment of the industry that was kind of over here and supplying the equipment in. I would say roughly 70% of that 20 billion is strictly for semiconductor equipment. So about $14 billion to buy the equipment. So it's a very heavy capital expenditure here. And by the way, of that semiconductor equipment, the biggest chunk of that 14 billion is going to be specifically for the photolithography equipment, right? That's the equipment that does the transfer of the pattern down onto the wafer. Here are a bunch of other things that you have to consider. These are just not normal buildings, right? You have to ensure that vibration techniques are used. A lot of these things, whether fabs in Taiwan have Taiwan's an island, right, that has earthquakes. And there's been a number of earthquakes there, and TSMC, UMC have constructed their fabs to significantly reduce the impact from things like that. You have a clean room environment that I talked about, and a multi-level manufacturing facility. Typically, it's going to be 3 levels, and the level up top will be for things like HVAC and all that stuff. The fab portion will be in the middle level, and then underneath you'll have chemicals and other things that need to be supplied into the process. All right, here's another chance for you folks to redeem yourselves. Okay, what do you think are some things that would drive whether a fab is profitable or not? I gave you a hint, by the way, right? Very large capital expenditures here, right? So
I was gonna be kind of obvious and just say profit and loss, but I guess
what drives that profit and loss? So let me put it another way. If you're managing a fab, what 2 things are you going to be looking at to decide whether you're going to sleep at night or not? Okay.
reliability and quantity.
Reliability. Boy, my brother Greg, if he's listening, he's a reliability engineer. He's going to love hearing that. But I'm going to have to say I'm looking for 2 other things. Let me give you. Oh yeah.
The cost of materials.
Cost of materials. No, but so let me give you a little hint. It'll be another industry. The airline industry, right? That's another capital intensive. Planes cost a lot of money, right? Do you ever hear about what happens when a plane takes off with empty seats?
Loses a lot of money.
Loses a lot of money, right? That same concept applies to wafer fabs as well. So kind of, what's that? Utilization is the term, right? And utilization basically says you build this big fab and it's got a certain capacity. Just like a plane has a certain capacity, 300 seats. If every one of those seats are not filled on the airplane, you're in trouble. Same here. If they don't have enough demand from orders coming in to build, then there's unused capacity. And by the way, it's just like a plane, right? Once the plane leaves, it's not like you can double book a seat on the next plane, right, to make up for that empty seat. Same in the fab. Once the day has gone, you're done. You can't overstart the next day based on increased demand that may have come in. So if your utilization is not running high, you run into a lot of problems. And again, it's because you have very high capital expenditure and you get these things called fixed cost reflow, right? There's some accounting rules that basically says if you can't take your depreciation expense and have it flow out as a cost of goods, basically, which is normally what happens, then accounting says you have to immediately take a charge to impact your bottom line. So the net effect is underutilized fabs can mean hundreds of millions of dollars impact to profitability. The second big thing is yield. And yield, 1 point of yield, 1 point of yield can mean 10, if not hundreds of millions of dollars on profitability. So to answer that earlier thought, if a fab manager is looking and sees that their fab is full and it's yielding well, they're sleeping very well. Yes, there's other things they need to work on, cycle time, reliability, some of the things you brought up, but these are two big drivers. In the interest of time, I'm gonna kind of go through all of this stuff here, but electricity usage, by the way, another big thing. Question?
Yeah.
Yeah.
So we saw that they have to use so much equipment, and like you said, that you just now electricity, like the size
Yeah.
of a small village. How do they handle, because I'm sure they're under fire a lot about like global warming, and how do they handle like limit,
Sustainability. Yeah, it's actually a big consideration in semiconductor industries, particularly around like water. In the
Mhm.
past, heavy use of water, so you see a lot of initiatives to recycle and recapture. Water is a big one. They also look at how they can be more sustainable with respect to energy usage,
Mhm.
right? And even some of the chemicals and gases that they use, they're always looking for things that are kind of more environmentally friendly, et cetera. But, if you go way back in the early days of semiconductor industry, unfortunately, there were some very nasty chemicals that were used. And they were literally dumped on the floor and, would seep into groundwater, et cetera. And it wasn't until years later, right, when they kind of discovered all this. Today, that's another reason why all this is done in very controlled fashion,
Mhm.
right? Whatever chemicals go in, they get recaptured, recycled, disposed of, et cetera. So sustainability, though, great question. Sustainability is a very big consideration, particularly if you think about the onshoring that's happening, right? Coming back to the US and now we have to deal with these things front and center. Packaging, I'm gonna accelerate a little bit because I also want to leave some time at the end for Q&A. These are sort of the classical ways where the chips would be put into various kind of packages, which allows them to be connected to the outside world. This is one, by the way, that you see today. So anyone who follows like NVIDIA and their AI and the chips that they're building, this is a architecture that they use where they have the NVIDIA chip combined with something called HBM. It's a special kind of memory. So they're putting like almost like a mini system together into a single high performance package. So this is an architecture that you see today for a lot of AI type devices. All right, quickly go through design. I talked about the design kits going into the designer. By the way, I started out as a designer 40 plus years ago. Yep, I was a mixed signal analog designer. And then I went to the dark side, as it's called, and went over to digital design. And when I did that, all of my mixed signal analog friends said, digital design, it's for people who can only count to one. So, a little electrical engineer joke there. But you have various steps here, similar to the various steps that you have to manufacture the process. I'm gonna accelerate a little bit here. Remember I showed you the design kits come in. So all the rules come in, and ultimately you got to provide design files to get it built. And very quickly, you'll also have front end and back end on the design process. And the front end of the design process looks very much like software coding, basically, right? You're doing some sort of requirements and design capture, right? And you're using various types of what I like to call software to define this out. And where you make the switch over from the software code into an actual design, a CAD file, that's when you go into the back end. And ultimately, you're going to provide this, and this is what goes into the fab. And what they do is they take, bless you, they take every one of the layers on here and they build that mask, and then that's how it gets stenciled and transferred, down on to the chip. I'll quickly talk about the other segment that was in there, because we talked about design, manufacturing, packaging, the semiconductor equipment, how important it is. But you remember there was also this group of folks that did software and intellectual property. These are blocks. Think of them as building blocks that you can purchase, pre-validated, they work, and it can accelerate your ability to design a chip. This industry, I put in there digital twin and shift left concept, because these, by the way, are two concepts I teach in my digital transformation class. And the idea of a digital twin, has anyone heard the term digital twin? So a digital twin, in the context of digital transformation, is a digital model that can mimic a real world product or process. So in fact, one of the popular nirvanas that people talk about is if we could come up with a digital twin of a human, ourselves, right? How would that be useful? You could test vaccines, for example, on this, do a simulation and get an idea of, is it both safe as well as effective, right? And you could even have a digital model of each individual. So not only would it be, humans in general, but you could see, for me personally, what will be the impact. Well, digital twins have been used in semiconductors, for decades now. And the way they get used, right, is these design kits, right, that come in. They have some complex digital models associated with them. They're simulation models. You've probably heard of things like SPICE and other simulations that you do. These things are all built and they're correlated back to the process that's been defined. And so the idea here is when the designer designs something and they use these digital models, they have a high probability that when it gets built, it will work coming out the other side. And this is going to be increasingly important because building chips is becoming a more and more expensive process. So you want to make sure that we talk about first time right. By the way, that was always the big celebration. When I was on the design team, when we got done and when the chip came back and if it worked the first time, right, big celebration. Obviously, it allows you to get to market faster, right? This is a big consideration. All right, I'm going to wrap up with a bunch of trends. Some of these we've already talked about. Diversification of demand, right? It's not just laptops and smartphones. Chips are going into everything, and increasingly becoming important for national infrastructure, right? So this is why you hear so much politics about chips, because people are realizing, we need them for defense, or we need them for our infrastructure of communications, 5G, et cetera, the internet, which is so important to us. There's a trend in personalization, which means, there used to be a lot less chips made, but a lot more volume on each chip. And now what's happening is because you're going into so many different markets, you're personalizing, which becomes a tougher job from a manufacturing standpoint, because now you're going to have to take down and set up more processes, and you got more part numbers to manage. It's more complex whenever you're dealing with personalization. The industry is bifurcating. So, I talked about Moore's Law, and for the longest period of time, we would just ratchet down and everyone would just jump to the next technology because they wanted more transistors and moving down. But right around, I think about 7 nanometer, which is, one of the defining dimensions, the industry started to bifurcate where certain things would continue on the Moore's law and going into more advanced technologies. Other stuff didn't. So the kind of things that did were processors and memory. The kind of things that didn't were things like analog devices, RF type devices, etc. They were actually perfectly fine staying in older technologies. So now, you have this issue of, we used to talk about SoCs, system on a chip. Everything would get integrated into a single chip. Well, now when you're not integrating it onto a single chip, you have to come up and still get the same kind of integration. And the way you're getting the integration is through that package that I showed you. So now you hear this concept called system in package, where instead of putting it all on one chip, you take multiple chips built with different technologies and you stuff them in the same package to achieve kind of the same thing. And this is what NVIDIA and other folks are doing with AI. Another thing that's also very interesting, this one for me personally, is this concept of vertical integration. And so what this means is, if you look at people doing the data centers, big hyperscalers. So this is people like Google, Microsoft, Amazon, Facebook, even to a certain extent, right? They're a big sort of internal data center, as well as automotive companies. They're looking at starting to do their own design work, so that they can design their own chips and not have to rely on buying them from other folks. Great example on this, by the way, was Tesla. Tesla in their first EV bought a whole bunch of chips from NVIDIA. And in their second generation, what they did is they're still buying some things from NVIDIA and others, but they've ramped up their ability internally to do their own chip designs. And what they do is they're sending those directly into the fabs to be built. So why is this, why did they do it? Well, there's three reasons on here. First is cost. At a certain point, I think you need about, depending on the chip, 3 to 4 million in volume is the break-even point, because to put a design team together inside your organization, today costs about $250 million a year, and it's rising. So you have a large fixed expense, but if you have enough chips and volume, it will at some stage actually be cheaper for you, because you're not going to pay the 50 to 60% margin to whomever you're going to buy the chips from. So cost savings is one. Differentiation, Tesla can design a chip for their EV, and only Tesla is going to have that chip, as opposed to them buying something from another vendor like an NVIDIA, and any of Tesla's competitors can get that same chip, right? So, and finally, supply chain control. And this was a big thing that came out of the automotive market, right? I mentioned COVID. Now, if you do your own design, you can interact directly with the manufacturer and say, this is how much I need, when I need it, et cetera, without having to go through the various layers. And geopolitics, right? Everything from the CHIPS Act to tariffs, right? Semiconductor industry is front and center on that. Here are three organizations, by the way, that are information.
Yeah, I have a question about trending.
Yeah.
I was wondering the trending of for example, like the stock market, like what's something like you think we should like look into, or like someone like as a freshman, for example, like which industry to like go into, like what's going to like develop more, like which company. So just because you said like it's expected to be like 1 trillion like in the future. So
everyone's talking. Yeah.
As someone who is like with more experience.
Sure. So the question, just in case we didn't hear it, was what industry would you recommend for I guess new grads or people going into college? What are some of the trends or hot areas? And we're right now, artificial intelligence, right? Everyone is talking about, and you can see the impact. Lots of companies are trying to figure out how to invest in it. They're sort of pausing on some of their hiring as a result of that, right? But one of the great comments I heard about AI was actually from Jensen Huang. Jensen Huang, by the way, is the CEO of NVIDIA. And he said, 5 years, 10 years ago, we were telling people, go study computer science. Everyone should become a programmer. And he said that, now the people that are going to win, that are going to be successful, are the people who can combine artificial intelligence with a domain expertise, like the physical sciences, right? Biology, chemistry, or other industries like agriculture, et cetera. And I definitely see that in companies that I talk with or consult with. They don't necessarily want just what I would call generic artificial intelligence knowledge. They want that combined with people who know how to apply it and to be able to solve a specific domain issue or problem. I mean, the ideal thing would be like, someone who's a agricultural AI specialist, right? Or a healthcare AI specialist. So that would be my 2 cents of advice and counsel.
Thank you.
Yep. 2 acknowledgements I have to do. I want to thank my wife, Janine. She's also a longtime semiconductor executive, mostly on the design front. So she made sure that the material you see here on the design side is correct. And then, of course, always looking over my shoulder is my older brother, Greg, who 43 years, I think, plus in semiconductor manufacturing. So he also made sure that the things I say on technology and manufacturing were correct. And that's the end. Other questions? Thank you. Thank you. Yes.
Yes, I had a question. You mentioned earlier when speaking that there's now a diversification of chips that are being required by the industry.
Yes.
And I would assume then that it's more difficult for profit since you have to make a more diverse amount of chips, which also would probably negate how many you can print or create. How is that being met by the industry? How is that the industry adjusting for that?
Yeah, so that's a great question. So the question basically is, given these, the term I'm going to use is explosion of complexity in building chips, how can you be profitable doing that? And by the way, I used that term specifically because that was a term we were using at Siemens. My last employer, I worked in Siemens Digital Industry Software. And the way we kind of turn that around is we'd go into customers and we say, we'll help you use complexity as a competitive advantage. And what we meant by that is the people who can figure out how to do and deal with this complexity, the different diversity of technologies, et cetera, the people who figure it out are going to win and win big. And the people who don't, they're going to lose and they're going to lose big. And, this industry has always been a, win-lose kind of industry. And specifically, this is kind of why I've also gotten so interested in digital transformation, because digital transformation, digital tools, software, the implementation of AI, all these things, semiconductor companies in every industry are looking at using this to be able to handle this explosion of complexity, as we call it. And you can go back in history with technology, by the way, and I teach this in my management information systems because most of the students in there, they're business students, and I'm like the lone technology class for them. And I tell them, this is the most important class that you'll take in the School of Business, because there's no bigger disruption in business today than through technology, first. Second of all, look at the largest companies in the world in terms of market capitalization. They're all technology companies. So, I think that the quick answer is you got to use technology and innovation in even handling this, but the rewards will be there.
So if I could follow up, so
Yeah.
then does that mean that by being able to accomplish that complexity, because that's not necessarily feasible by every company,
Mhm.
we're able to make up for that demand by maybe demanding more or being able to.
Absolutely, absolutely. Yep.
Thank you.
And, you get higher ASPs if you can do that reliably. Look at TSMC, for example, right? TSMC, one of the premier foundry manufacturers that's out there. And, they, as a result of that, they command a premium on their ASPs. And of course, when you apply that premium across this big volume that they're doing, even if it, a lot of different things, but overall, they're one of the most profitable manufacturers out there. It also allows you to garner market share, right? Because that's the other piece. It's not just the price you charge, but if you get more and more volume in, it allows you to also build more fab sites, right? And invest more in capacity. And, everybody wants profits and market growth. Yeah. Question over here.
Yeah. Going back to the chemistry and
Yeah.
in your experience in the industry, in your experience, what would you say is the share of the industry dedicated to R&D, and more specifically, the research of these new metals or elements to use for semiconductor manufacturing, better, to improve designs, to overhaul the design completely, even maybe,
Yeah.
depending on the properties of this.
So let me see if I captured it correctly. Of the 120 billion that I showed in the industry, how much of it is specifically going into the technology
Yeah,
piece?
or when operating in the company.
Yeah.
How big is the R&D department while you're working, even if you're not working in the department itself, what you hear working in the
Sure.
company about them and like
Sure.
what they're working on.
Yeah,
Right.
so I will tell you that, so first of all, on the 120 billion, the bulk of that is going to be in the technology and manufacturing piece. So if you looked at the TSMCs and the IDMs that are on there, the Intels, the Samsungs, et cetera, the bulk of that 120 billion is going to be in the manufacturing side. Now, there is some on the design piece, et cetera, but not as much as on the manufacturing side. In the manufacturing environment, they are, so they're typically closely coupled in with the production, right? Because, again, when you look at some of the people who have been more successful in doing this, they develop technologies with the intent and knowing that eventually these things are going to be put into production. So when you're developing the technology, for example, one of the things, I showed you what was really important, semiconductor equipment, right? So expensive. So when you develop a piece of technology, you also have to have in your mind that, okay, this technology has to run on these types of equipments, and this is what's going to be in the manufacturing line, et cetera. So the companies that do that the best, typically have the smoothest, what I call NPI and scale process. NPI standing for new product introduction, right? They develop a technology, and it's also, it can be common to have rotational assignments, right? Because it's always good for development folks to have experience in the manufacturing line and manufacturing people to get the opportunity to work in development. And so I think particularly in the manufacturing side, they try as much as possible, right, to have a close connection. But then, once you do get into production, right, you do also have to have kind of a different mindset, right? The process then becomes locked down. And you don't want to actually be changing anything or fiddling with it, because now you're in a production mindset, right? Which says, I need to be focused on cycle time, reliability, yields, et cetera. And, that's a different mindset when you're trying to tweak or optimize a process. But, the other area that typically will happen too is if there's an issue in manufacturing after 6 months or 9 months, it could be typical to pull a research or developer in to help debug, what's going on.
Good. Thank you.
Yeah, thank you. Other questions? Yes.
Given the industry or like the state of the industry right now, what would
Yep.
you say is like the importance or rather, I guess, the role of like the intersection of material science and electrical engineering for that innovation?
Yeah, I think that's a great question. Well, I'll just explain. So on one of the slides, I talked about introduction of new materials. So silicon, for example, on the base wafer has been around forever as sort of the mainstay. But increasingly, you see things like two big ones are gallium nitride and silicon carbide. And both of these, gallium nitride, by the way, came out of the, I think the LED lighting sort of business, and its ability to handle, for example, very high temperatures reliably. So you see that. Silicon carbide also has similar properties. And so that's one intersection point that's really important today. And again, because of the diversity of demand, right, it's kind of driving that piece. Another area in the question you had about sustainability. So there's a lot of work looking at, alternative elements, chemistries, et cetera, that, are more sustainable. I think back, for example, in packaging, there used to be a heavy usage of lead in semiconductor packages. And now, through a lot of global initiatives, because of the issues with lead, right? We got it out of paint, we're trying to get it out of houses, we need to get it out of semiconductor packages. Lead is pretty much, I think, eliminated from most semiconductor packages. So that's another sort of area, around material science. Are you a material scientist?
No, I'm a ECE. But
ECE.
yeah, I
Yeah.
like material science, so.
Yeah, it's, the other appreciation you probably got from this, right, is how things are sort of morphing together, right? I mean, the process of building these chips is very much a chemical process. The design process, obviously, probably a lot of you have done some various types of design work, but you're starting to see chemical engineering, electrical engineering. The packaging is very much a mechanical, right? You've got thermal characteristics and reliability that you have to deal with. Civil engineers, very involved in the building of the fabs and whatnot. Chemists, material science. And what happens is, right, as the industry grows, as we get to this march to 1 trillion, you're going to keep pulling in sort of more and more folks, even folks from like retail and consumers products, because, for example, what they're very good at is understanding forecasts, right? When you're someone who's working in retail consumer products, you're looking at what does the forecast and demands look like? And so a lot of these people have been brought in because, by the way, if you look at some of the consumer electronics, like phones are, it's almost like it is a consumer product at this stage, right? And so as a result of that, it's very important to understand what are people's mindsets to this, because that forecast of that consumer product blows all the way back to a forecast of chips that are going to be needed. And I told you, one of the big things you got to think about as a fab manager is utilization, right? So all this stuff is tying together. Other questions? I know there's food in the back, so it's gonna, I know what that means on campus, by the way.
I have another question.
Sure.
About that, but, so I know that we've seen like a series of tariffs and stuff like recently. Is that causing maybe a slowing in production or, are prices rising from that? Or are we also seeing an initiative into looking for new materials that could be used?
I don't think we've seen the impact, first of all, tariffs yet. And by the way, trying to implement tariffs in the semiconductor industry is a bit tough because, well, I talk about the diversity of demand, but let's just focus on the laptop and smartphone as an example, because they still, I would say, generate the bulk of the volume in there. So most laptops and most tablets, laptops and smartphones are built outside the United States. And the delivery point for the semiconductor is generally outside the United States. So, take Qualcomm as an example, right? Qualcomm designs a part, and one of their big manufacturers is TSMC in Taiwan, right? So they send the design over there, it gets built in Taiwan, and then it could go to China, or it could go to Korea, Indonesia, Malaysia, a bunch of places to get packaged. And then it's going to get delivered to, say, Samsung. It's going to go into a Samsung phone or Apple, right? Well, the sale point is going to be over somewhere in Asia, right? So it's going to go into the phone, et cetera. So all of that basically is not captured from a tariff perspective, right?
Would I be able to tweak my question? I think I
Yeah.
phrased it quite poorly, but what I meant more was, like, in terms of between various countries, obviously there are trade
Yeah,
becoming a little bit more complex, particularly now that we're seeing materials start to become less accessible.
mhm.
Is that like also providing an impact on that industry at all, or have we not seen that yet?
So you're thinking like rare earth materials and
Just generally, yeah.
Yeah.
and, like, what materials would be used to create those?
So I would say it is clearly a consideration in geopolitics, right? So, you hear a lot of people talk about, we want to onshore manufacturing into chip manufacturing into the US, right? We got all these fabs coming up. But that's only a piece of the equation, right? Because there's a bunch of raw materials that you need to build these chips. And by the way, there's the end part of the supply chain that I talked about, right? Where you got to package it. And then it's got to get delivered to the customer, and most of the customers are not here, right? So that's the little bit of what I call the fallacy around the politics, if you will, of, the supply chain. So on the materials side, it is a big issue, right? Because no one country, and certainly not the US, right? We're actually not very well positioned with respect to all the materials that you need. So, what does the US do about that? A few things. They try to form alliances, obviously, with countries like, even the Ukraine, right? They were trying to force an agreement to get access to, Ukraine's got a lot of these things, places in Africa, et cetera. So there is some of this scurrying around, I will call it, where people are trying to, form alliances, and you're getting a little bit of a east versus west on that, which is frankly, I think unfortunate, because one of the things that really allowed the semiconductor industry to kind of get where it got in terms of innovation was global cooperation. And we're kind of going backwards a little bit on that. But yeah, it will be, some things that'll have to be looked at here. Just to finish off the tariff comment, right? That one, very difficult to understand how it's going to be enforced, et cetera. I don't think it's impacting anyone's decision-making per se on, I'm going to, manufacture, more in the US versus what's already been announced. Primarily because these tariff things, they can quickly change. And when you're talking about capital expenditures that are in the tens of billions of dollars, most companies are not going to just make this based on the fact that, oh, there's now a tariff here, right? So we'll see how all of that plays out. It's still very much, but on the material side, yeah, people are trying to look at, can I use alternative materials and stuff, but the thing that worries me more would be if we get another bifurcation in the semiconductor industry, which is an east semiconductor industry versus a west, right? I really would not like to see that happen. Other questions, or do we, anything, by the way, online? I don't know if anyone.
No questions online.
Okay, great. Otherwise, we can stop and
And thank you so much for taking us on this engaging journey.
My pleasure.
Let's thank our speaker again.
Thank you. And for all of you as well. Thank you very much.
Sure.